talk about big operators in ADS5 CFT4, which is a slightly different title than what had been announced.
Thank you. Thank you very much. It's a great pleasure to be here. It's a pity we cannot meet in person, hopefully very soon. And thank you very much for the invitation to speak. The title is a bit different, but it means the same thing. It's just I forgot what the title was, and I was just writing it this morning.
Absolutely.
But so it's about big operators, not too big. They are not going to scale with n, but still very big operators in n equals 4 super-Young mills. Because as I will tell you, when operators are big, we can make some analytic progress in trying to understand better the structure of this theory that we very much want to solve. Okay, so let me tell you a little bit about what I'm going to do, and please do interrupt me if you have any questions at any moment. So we are going to describe, always be considering BPS operators in n equals 4 super-Young mills, half BPS operators. So our operators will be the following. So we have the 6 scalars of n equals 4 super-Young mills, phi I runs from 1 to 6. So these are the 6 scalars. We evaluate them at a single point in flat space. And we contract these scalars, we make a linear combination using a 6-dimensional null vector. Then out of this combination with this complex scalar, we take k units of this object. So this will be an object that will have dimension k. We call this guy OK, and we take a trace to make it a gauge invariant operator. So these are the operators we are going to study. These operators are half BPS. Their dimension, as I said, is precisely k. They are parameterized by these 2 vectors, a null vector that tells us in which direction it's pointing, and position space that tells us where we are inserting this operator. And we will be considering this k here to be large, and let's discuss in a few slides how large it is. But it's going to be large, it's going to be a big number. And the key objects we are going to consider would be something like correlation functions, where I consider computation of, say, k1, up to, say, k4. 4 will be the one that we'll be focusing on. So this would be a 4-point function in n equals 4 super-Young mills. And that would be the key object that we would like to study. Now, if we think from the point of view of ADS, if this is ADS, putting one of these operators, inserting one of these operators at the boundary of ADS, this would be the boundary of ADS here, which is the flat space where we insert the operators. And then these operators would insert some closed string here. So they correspond to inserting a closed string. So this operator would insert a BPS closed string, or we can think of it as some supergravity mode, especially depending on how big k is. And here we could distinguish, of course, 2 obvious cases. K could be of order 1. So if k is of order 1, then we say that this would be a light operator. Or we could have that k could be much bigger than 1, and then we call these operators heavy. Their dimension, their energy is very big. And often we distinguish 2 cases. We distinguish further. When the operator is heavy, it can be heavy in different, it can be very, very heavy, or it can be just heavy. So let's distinguish 2 further cases. Suppose we are in the regime where the 't coupling lambda, let's go to the regime where lambda is much bigger than 1. This would be the large radius limit of ADS, the strong coupling limit of the gauge theory. Then we could imagine, for example, scaling this k as lambda to the 1/4, or scaling it as lambda to the 1/2. And as I'm going to review, this lambda to the 1/4, this corresponds to short strings, whereas lambda to the 1/2 corresponds to large, will correspond to large extended string objects. Okay? And the intuition here is, as I said, this k is like the energy of the operator I put. So k large but not too large would be like low energy. K large and really, really large is like high energy. And just to make this intuition even more precise, let's remind ourselves of how things work in flat space with respect to scattering in flat space. Because, okay, let me emphasize this basic thing. So what we have here, this is like a process of scattering in ADS, right? It's the analog of scattering, but in ADS. I have 4 points at infinity, which is the boundary of ADS, and I send them in and they interact with each other. And so how does it work in flat space when we have, let's review a few things, a few simple things about Virasoro-Shapiro. Okay, let's hope I have space. I want to write a few things. So let's suppose I have my Virasoro-Shapiro amplitude, Virasoro-Shapiro. It depends on the Mandelstam invariants, S, T, and U. Of course, they are not independent. S plus T plus U is equal to 0, but it's convenient to write it as a function of the three to highlight crossing symmetry, which is permutation of these objects. And then, well, we can package various particles that are related by supersymmetry by factoring out some supersymmetric delta function. Picking various elements of this delta function would tell you if you want to scatter the graviton, the excidilaton, and so on. What do you want to scatter exactly? Then there is this famous factor STU. So this result here is the supergravity result. And then there are these famous gamma functions. So gamma 1 minus alpha prime S over 4. And here gamma 1 plus alpha prime S over 4. And then there is a similar expression, the gamma functions with T, and similar gamma functions with U. Now, what does it correspond here? What are the two limits we could take here? Well, one limit we could take is the field theory limit. This would be the low energy limit, where alpha prime times S is much smaller than 1. Right? So we take this limit where the energy is very small. And what do we get here? In that case, this gamma function factor here. As we take low energy, it's convenient to write an equality where these gamma functions, they are exactly equal. Here there's no approximation, but the approximation is in keeping a few terms of this expansion. It's equal to a sum of an expansion in alpha prime. So there will be powers of alpha prime here. There will be here some powers of energy. So S to the 2n plus 1 plus the same thing with T plus the same thing with U. And here there are the coefficients of this expansion. They turn out to be related to odd zeta functions. So there is zeta 2n plus 1 over 2n plus 1. And this sum runs from 1 to infinity. And of course, the first few terms of the expansion represent the first terms in the low energy expansion, what we would get from correcting supergravity with higher derivative terms. So this is, of course, very well known, and many people like Michael Green and collaborators have studied a lot the nature of this expansion and all these zeta functions, and even beyond this, how they talk to G-string corrections. Then there is another limit we could take. Let's go up here, which would be the high energy limit, where we would take S, T, and U all scaling in the same way and very big. And we want to take now alpha prime S to be much bigger than 1. And this regime is less familiar to most, but was also a regime considered by Gross and Mende. So this would be a regime that Gross and Mende considered a long time ago, where we are scattering strings at very, very high energy. And because the energy is so huge, we send these huge energies and we excite all the modes of the strings, and the strings open up and they become big. So the relevant path integral configuration that dominates the string scattering is that of a big classical string that and not a point-like field theory interaction. So how does the result look like in this case? These same gamma functions, let me write them now, another equal sign, but now it will be another expansion, saying that these gamma functions are equal to the exponential. And then there is here a term, which is the area of this big classical string, something alpha prime over 4, S log of minus S, plus the same thing with T, plus the same thing with U. And this is what we would say, this here is what Gross and Mende computed. So let's call it the Gross-Mende minimal area. Okay. So here from the gamma functions, this is just Stirling approximation. We just take alpha prime has to be very big with what Stirling approximation, and we get immediately this result. You can also obtain it. You just have the 4 vertex operators, and you integrate over the position of the fourth one. But the position of the fourth one, when the energies are very big, is localized by a saddle point, and the result of this saddle point computation would give you directly this Gross-Mende area without going through the explicit gamma function. Now, what you could do now also is not stop at the saddle point, but capture the fluctuations around the saddle point and all corrections around the saddle point. And this would lead you to another identity for these gamma functions that, to my knowledge, people did not write before, but of course it was known for sure, which would be an expansion at high energy around Gross-Mende. And now the expansion would be in inverse powers of alpha prime. The powers of energy are inverse powers of energy, plus the same thing with T, plus the same thing with U, as usual. And the coefficients now are Bernoulli numbers, with some n and n minus 1. And in fact, it is fun to note that these terms here, these Bernoulli numbers, and these zeta functions down here are actually not independent, and they are in fact analytic continuations of each other. So if you take these zeta functions and you continue them to negative values, you get this Bernoulli number. So technically, one way of understanding these two expansions at once is writing the gamma function as exponential of some integral representation. And that integral representation, if you close the contour to one side, picking all singularities, you get one expansion. You close it to the other side, you get the other expansion. And because the integrand is the same, the two sides will be analytic continuations of each other. Okay, and this would be how you could, in this funny way, go from a high energy expansion and a low energy expansion. So these Bernoulli numbers capture all the information about the moduli space, because the saddle point was fixing one point of the integration over the fourth point. But then the fact that it is not just one point, but all the moduli space that matters is captured by all these Bernoulli numbers that in principle we would have to keep if we wanted to get the full result. And I'm highlighting this because as I'm going to explain in a few pages, when we study this process in ADS-CFT, we can scatter some operators, and there could be some region which looks like flat space if the strings scatter in a small region. And when they scatter in a small region, depending on how we approach it from ADS, from very big operators, very small operators, we could make contact with strings in flat space coming either from the high energy corner or from the low energy corner. So it's good to have in mind both expansions because we might want to meet flat space from different directions. Okay, so let me just draw a picture again. So a picture for what we just saw. We just saw that we have this axis of energy, right? Which is like, again, it's morally speaking like our K, that we have here we have the full Virasoro-Shapiro amplitude for intermediate energies. And then for at low energies, the strings become effectively point-like, and we have low energy supergravity and corrections. Whereas at high energy, the strings open up and you have some big strings scattering with some big opening of the strings. And here you have Gross-Mende and its corrections. And there is a nice interpolation that we can understand in all possible ways because we have here an analytic expression. Okay. So now, what about ADS? So in ADS, we don't have the analog of Virasoro-Shapiro. We don't know how to compute the correlation function of 4 operators at any value of the string tension, which would be at any value of the 't coupling. We don't have that expression. And of course, we don't have 1/n corrections, which would be G string corrections. So what do we have? What about ADS? And in particular, what about these correlations that we are studying? And let's define them to have all the same P. Just for simplicity, suppose I have 4-point function. And suppose we want to consider this at lambda very large and at n going to infinity. So n is the biggest one. So we are just doing planar now. And I will comment on genus 1 a bit later, and I can comment on higher genus at the end if people want. But we are going to focus on strong coupling, which is the regime where ADS is big, and n going to infinity. And now I have, if you want, the main take-home picture of what the physical picture should be. And here we have, before we started with the formulas and then we made a picture because we had full control. Here we start with a picture and then we'll try to come up with the formulas if we can, because ADS is much harder than flat space and we cannot solve everything. Okay, so here would be the physical picture for the various regimes, how you should think of these correlation functions, depending on how big these operators are. So if we start with small operators like p equals 2, p equals 3, we are describing low Kaluza-Klein modes of the graviton. So we are just scattering our gravitons in ADS. It is just supergravity. So here we would be studying some process that is not localized in any point in ADS, and you have supergravity in ADS. Okay, then P starts to be large. And when P starts to be large, what happens is that these interactions, they want to propagate towards a region, maybe you cannot see, so towards a region, which would be the interaction region. So this would be, you can think that this propagation of these propagators become classical geodesics, and they meet at wherever minimizes the cost of this propagation. And so there will be some region of interaction, P, and the Feynman diagrams, in this case, the Witten diagrams, would be localized close to this point, so clearly in starting to approach a flat space limit. This would still be in supergravity, but the diagrams would start to simplify and localize. Then we reach a regime where P is of order lambda to the 1/4. It's very big and it's scaling with lambda in a particular way. This, we will see in explicit formulas later, corresponds to reaching a regime where, again, we are interacting in flat space, and we are, as an expansion in X, we are having access to the low energy expansion of flat space. So this would be how we would enter flat space and make contact with all these odd zeta functions that we arrive at low energy. If P over lambda to the 1/4 is X and it's of order 1, then we would still propagate as close as very short strings, almost particles, until an interaction region. And then in the interaction region, we would have the full strings Virasoro-Shapiro amplitude. If this parameter X is very big and P scales with lambda, now they would propagate still as short strings, but when they reach the interaction region, they would open up and form an open classical string that would be given by Gross-Mendel still in flat space. And finally, if P is of order square root lambda, then there will be huge centripetal force when we send these strings that will open them up and they will fill the full geometry of ADS. And so here we would be in a regime that would be like the analog. So it would be a minimal area in ADS. Okay. Now these minimal areas in ADS, so were not computed yet, even though it's a purely geometrical problem. So the problem is very well posed. You have a sigma model. It is just a map from 2 dimensions into ADS 5 times S5, right? You have this very simple sigma model. But however, the sigma model is very nonlinear, and finding these minimal area solutions that end on 4 points at the boundary and that are big extended strings, this was not solved yet. So João Caetano and John Toledo solved part of the problem. They computed a bit half, you could say, of the result. This area contains an ADS part and a sphere part, and they computed in some cases the ADS part. But the full computation of this area is not yet known. So we cannot, it would be very nice if this was known. Then we could start with this result and start taking P decreasing p. So here we would start taking p over square root lambda to be small, and we would make contact with flat space. So this is something for the future. So what we are going to do instead is start from supergravity and try to increase p and take p to be large and see how far we can go, and we would enter flat space through this other corner here. And I will only make some comments about these really big operators that generate these big classical areas at the very end. Okay, but just to say that there has been some recent progress about these minimal areas, mostly from Frank Coronado, who understood from a different point of view, using the integrability of the problem, how to get an expression for some of these correlators at any value of the coupling. And in particular, he could then take the limit of very strong coupling to get an expression that does exponentiate. And so we identify the exponent as being a minimal area. It was not yet computed directly from the sigma model to check that this result is indeed a minimal area. Okay. So let's do that. So the idea now is we start with our 4-point function. And we will take the results that people over the past years have been computing. People have been studying using bootstrap techniques and developing further supergravity techniques using Mellin space. There is now data. There are 4-point functions. Mostly typically people consider p to be small. Typically p is equal to 2 is the simplest case people study. But now the technology is better and people have been studying also general p. So we can use this new tool to try to study how the 4-point function would look like when we start studying p, which is larger and larger, so that we can get this 10-dimensional flat space structure. Okay, so the 4-point result, it's convenient to write as the free result, what you would get in free Young-Mills if you set g to 0. Then there are some simple kinematical factors. These are just 1 over x minus x1 minus x2 to some delta powers and so on. So nothing, and some supersymmetric delta functions, the analog of the supersymmetric delta functions of Virasoro-Shapiro that I showed before. And then there is the interesting part, which would be an amplitude that depends on p. Remember, we are taking all operators to have the same weights. And now it doesn't depend on positions and null vectors, but only on cross ratios, on what is left invariant under the conformal group. So these are the cross ratios. And there are 2 cross ratios, u and v. And there are 2 R-charge cross ratios. We can call them u tilde and v tilde. So this u would be something like the difference x1 minus x2 square, x3 minus x4 square, divided by something like x1 minus x3 square, x2 minus x4 square. And u tilde, for example, would be similar with xi minus xj square replaced by these null vectors yi dot yj. Okay. And so this AP is the object we want to study. That's the interesting part, the part that carries all the physics of this correlator. So that's the object we would like to study now. And so the first thing we did with Francesco Aprile was we wrote this A here. We understood that this A, as I said, people have been studying it in Mellin space, but we understood that it's convenient to write it in a more ADS5 times S5 friendly, this AP, by writing it as some kind of super Mellin transform where we introduce some parameters ds, dt, but two new guys, ds tilde and dt tilde. So these guys, the first 2 are the standard Mellin variables. These guys would be what we would call the sphere Mellin variables. And let me tell you what the definition of this is. So this is just a transform. So it's roughly a Fourier transform of these cross ratios, or of the logarithm of these cross ratios. So there is something like u to the s, etc. And then the last one, v tilde to the t tilde. So these s, t, s tilde, t tilde are conjugate to u, v, u tilde, v tilde. Then there is some gamma functions that I'm not going to write because there are too many, but let me indicate this symbol to indicate many gamma functions. So here I'm hiding, I think it's 12 gamma functions. And I'm going to tell you what they do here, but it's some simple gamma functions of S plus T minus P, things like that. So this is totally determined. It's a definition of the object. If you want, you define this. So it's a function of S, T, S tilde, T tilde, but it's defined. And then times, and now instead of A, what replaces A would be the Mellin variable MP that depends on S, T, S tilde, T tilde. So it is just a transform, as you see. Okay. So, so these gamma functions, they have poles. So what's the physics? What's the meaning of these poles? So this gamma function has poles, and this MP, this one has poles in S and T, but not in S tilde and T tilde. And this one has poles in all variables. And so what happens is that when you write this integral, first the poles in S tilde and T tilde transform these sums here. This integral becomes a sum, becomes a discrete sum, if we pick the poles. So this is to be expected because the sphere, the object we started with, is by definition a polynomial in these polarization vectors wise. There are a finite number of structures, so it should be a sum over all these possible structures, right? And so there should be a finite but big sum, big because since K is very big, there are many structures, but it should be a finite but very big sum. And indeed, these gamma functions are such that its poles precisely give you the sum that you want to get. S and T, they have poles coming from both the gamma functions and M. You see that poles in S and T will give powers of U and V, which are basically OP, an OP expansion. So the poles here, so poles here, they correspond to the operator product expansion in either channel, depending on how you close the contour. You could get poles in U or poles in V and so on. So schematically, what we have is we have some kind of integral, as I said, and then there are the poles, and deforming the contour and picking the poles. For example, this could be S. Picking the poles in one direction gives you a U channel, an S channel OP. Picking in the other channel, we have a T channel OP. And there are many poles, and you could have many families of poles, and you are doing some kind of contour integral. And this is a bit schematic because it's a multidimensional thing and so on. Now, what happens when we take P to be very large is that the object is not dominated by these poles, but rather it will be dominated by saddle points, that complex saddle points that will be somewhere else. And so what will happen is that you will deform your contour to pass by these saddle points. And then your amplitude will be dominated by the value around this saddle point. And then it will simplify dramatically this expression because all these integrals here will become just totally localized by their saddle point expression. And so I prepared the expression here. So here is the result that we get. So let's digest it a little bit. So the last factor, it's obvious. It is just, I said that I have an integral of the Mellin amplitude and I evaluate it at a saddle point. So what do I get? I get the Mellin amplitude at the saddle point position, right? So that part is obvious. And here is the value, for example, of the saddle point. If I do the saddle point equations, I get this S star, for example. So this, I would call this S because it's related to the cross ratios U and V. I would say that this is an ADS saddle point. And there are similar saddle point equations for S tilde, T tilde, and so on that I would call sphere saddle points. So I take my Mellin amplitude and I evaluate it at the values dominated by this saddle point. And then I have another factor that comes from this gamma function that was this gamma infinity, and also from the quadratic fluctuations around the saddle point. And so that would be, oh, I lost that. That would be this first factor, the first line. And now we want to identify this with some physics. And the proposal is that this first factor here, we should think of it as propagation in ADS5 times S5. Okay. So, and indeed, you see that this expression really looks like there are some parts like this one, which is ADS, and then some part like this, which is sphere, some part like this, which is ADS, some part like this, that is sphere. So this part really knows that it's a product of two spaces. There is ADS5 and there is S5. And then there will be this bottom part, and this would be describing interaction, the interaction part, and the interaction part now happening in this flat space region, in 10-dimensional flat space. Okay, and that's the claim that, that we have. And in particular, we will see that for this to be true, this Mellin amplitude better simplify. And instead of having these variables for the sphere and variables for ADS, they should combine into nice 10-dimensional variables. And indeed, we will see that here we will have an S 10-dimensional, which would be S plus S tilde, etc. And the claim is that at large P, this object here now will only depend on 10-dimensional objects. Okay. So for example, let's do a check, a sanity check of this. For example, this Mellin amplitude has been computed by Rastelli and Zina and Zhu at 3 level, which means large lambda and n to infinity. So here would be n to infinity, the planar limit, and 3 level and the leading power at square root of lambda. So it's really the leading term that would correspond to the 1 over STU in flat space. And what do we find? We find that for any P, actually, it's possible to write this result in a nice way, which is 1 over. And then using these 10-dimensional variables as 10D, you get 1 over S 10D minus 1, 1 over T 10D minus 1, 1 over U 10D minus 1. Okay. And then you see that this definition of S 10D is the sum of S plus S tilde, the sphere, and the ADS minus some variables. And at the saddle points, they are big. P is big. So these variables are big at the saddle point. And so this expression, which so far is exact, this is for any P. When I evaluate them at the saddle point, it becomes exactly 1 over S T U as in Virasoro-Shapiro supergravity, right? As in 10D flat space supergravity, okay, when they become large. And more generally, the proposal is that at large P, MP will be 1 over this 10-dimensional S, T, and U times the rest. Let's call the rest S. The rest, by the rest, I mean this stuff here. All these gamma functions, and also the 1 over n corrections to it, the G-string corrections will claim everything. So there would be all these variables of these 10-dimensional variables, S, T, U. There is some prefactors, some Jacobi, some factors here, and so on. And so that's the proposal on how this 10-dimensional symmetry would appear here, and how these variables are quite convenient, even at finite P, as you see here, but especially at large P to see this emergent 10-dimensional symmetry. This statement, by the way, that was made by Karanwot and his student recently, which was the statement that at large n and large lambda, there is an emergent 10-dimensional conformal symmetry that allows to package all objects in a very 10-dimensional way. And here we are making the statement that that enhancement occurs also at any value, at any term in the 1 over lambda expansion and at any value of 1 over n, if you are considering big operators. Of course, not if you are considering small operators. If you are considering small operators, as we said, we should really fill the sphere and so on. So finally, I wanted to do a small computation, but I see that my time is running out, so I will not do, I will just tell you.
You have about 4 minutes.
Yeah. So I want to just tell you this because I want to comment on the picture, on the big picture. So another check we can do of this picture. So this was what I just described to you was an explanation of this interaction part. And what we did to confirm it further was take all the results in the literature from this bootstrap and localization and so on for 1 over square root lambda expansion to check this picture. And we also computed some genus 1 Mellin amplitude that would describe a 1 loop supergravity, and we also checked it against, and it works. But what about this propagation part? Is it really true that I can identify this part as propagation? So there is a very nice exercise you can do where you start with a Witten diagram and you have an interaction point, and these yellow lines represent exponential of the length of the geodesics. You find the minimum and you evaluate the action of this length of the geodesics at the minimum, and what do you find? You find precisely this factor here with the 2p, the exponent 2p. So that comes precisely from just the propagation of these factors up to the interaction point. And then it's quite nice that you can even do a little bit better, and you can do fluctuations and study the fluctuations around this saddle point. And that gives you exactly these prefactors here. And so this factor indeed can be identified with a propagation to a midpoint and its fluctuations of this propagation to an interaction region. Then when these short strings meet in the interaction region, instead of putting just a contact diagram, we insert the full flat space S matrix. And that's the final prediction for what the picture should be. So let me go back to this picture and highlight that. So what we are saying here is that as I'm increasing k, I'm going into a regime where I have small strings coming in. There is some propagation and fluctuation that is given by that prefactor coming from those gamma functions in Mellin that governs the propagation and fluctuation. And then they reach the interaction part, and instead of putting a contact interaction, we should put the full 10-dimensional S matrix. Now it will be very interesting to carry further. So if we resum everything, we can get all the way to here or here if you want, to this Gauss-Mende, but we can't get past. If we start increasing further, then this expansion is not controllable. If P is bigger than lambda to the 1/4, then what we were doing, thinking it was a reasonable expansion at strong coupling, breaks down, and you need to resum everything if you want to see these big extended strings. And the hope that we have is to start from integrability from this side and lower it in this direction, which is some work in progress that we are working on now. And the hope is that in doing that, we will get a full coherent picture of these correlators at strong coupling and for any large P, that we hope will also shed light over the finite P structure. If you want to have the full result for these correlators at any value of P, which is, I think, would be the most fundamental object in N equals 4, these 4-point correlators, then having these boundary values for what should happen to them at large P would be very important. And of course, it would also be very important from the point of view of just understanding better holography and flat space holography and this flat space limit and this interpolation between low energy and high energy, even in flat space. So yeah, let me just end by saying that yeah, and I think I will end here. If there are, we have 20 minutes for questions. If people are interested, I can develop further on any point. So thank you very much.
Any questions? Please raise your hand or ask the question in chat. Questions? I'm not seeing any questions. If you have a few more remarks you'd like to make, you're welcome to do that, Pedro.
I have a question.
Oh, yes, please.
Thanks for the nice talk, Pedro. So just about this enhanced 10D symmetry, what is the leading correction in this large operator discussion that breaks this enhanced 10D symmetry? I think you're muted.
Pedro, sorry, I muted you. I muted everybody.
Sorry, yeah. It will be keeping one of the, it will be keeping one of these ones, right? Instead of keeping just STU, would be, no, sorry. There are two different questions, sorry. One is, so your question was, when do we see the breaking of a 10D symmetry at finite P? So we see it right away. So it's only there really at the classical level at the planar limits. As soon as you go beyond, there are some terms that still somehow have this symmetry because they are just like iterations of tree level. Like if you just put two tree level together to get a discontinuity of one loop, then okay, some parts of that discontinuity will have this 10D symmetry. But if it's not some simple recycling of tree level, then the symmetry breaks away right away. So it's an accident that classically flat space is conformally equivalent to ADS5 times S5, right? They are related by a wild transformation. So if you are lucky enough and your process is not sensitive to this wild map, then you can get the same result, but normally you are not, so it should break right away, and it does.
But in this large P limit, it will be restored, right?
At large P limit, it will be restored, yes, because
But,
then really it is restored in the sense that the result really factorizes into one part, which is not at all 10-dimensional flat space, right? It's really propagation. It's really it's function of sphere over function of ADS. It couldn't be more ADS5 times S5. But then it factorizes into that times another contribution, and this contribution restores this 10-dimensional symmetry.
Right. So I have a related question. So this 10-dimensional piece could in principle contain terms that are non-analytic in the STNU.
That's true, and they do. So for example, at one loop, you start getting the box in ADS, and you start getting logs of -s and logs of -t and so on.
I see.
And there is no contradiction because you see that we started saying that the Mellin amplitude is a meromorphic function. It just has poles, right?
Right.
But we are not close to the poles. We are here, far away from the poles, right?
That's
so
true.
We are here, far away from the poles. So as you go far away from the poles, from far away, these poles, it's not uncommon that these poles can look like a cut, for example. And you can form effective singularities just by condensation of poles. It happens all the time in matrix models, say, right? You have many eigenvalues and they condense into cuts and stuff like this. So that's the mechanism as well here. You have these Mellin amplitudes. At finite P, they are just meromorphic functions of S, T, S tilde, T tilde. Then when you go to the saddle point, effectively, they can become arbitrarily complicated. And you develop all these cuts and all the structure that we expect for scattering amplitudes with all these non-analytic terms.
Right. Thank you. I have a follow-up question, if I may.
Sure.
So this 10T symmetry would be probably absent in the other case, like ADS4 or ADS7. But I guess most of your construction will still go through.
That's right. So
M theory S matrix that you should insert.
That's right. So the enhanced the finite P enhanced symmetry should always be there because it is just equivalence principle, right? It's just we scatter at very high. If we scatter in a small region, it looks like flat space.
Yes.
Right. So I agree.
But there's no string Wolf sheet anymore in the in a very large P limit anymore because it's M theory.
Right. So we should see some difference in the yeah. So here when I was describing, for example, Gross-Mender, right? So where do we see that there is a big world sheet? We see that this expression at large energy has this big area term, right?
Yes.
Somehow that information is hidden in this expansion at low energy, right? Because if I keep the full expansion, it's the full result.
Yes.
So from M theory, we will end up on an expansion like this, but instead of these zeta functions, we have something else, right?
That's right.
But somehow it's a very different expansion because that expansion, if then we take the opposite limit, should not exponentiate and give some minimal area because as you see, because of what you just said, right?
That's right.
It gives something else, and I don't have a good intuition. I don't have an intuition about what this expression, how this. I mean, as I said, these are analytic continuation of this.
Right.
So if in M theory we have some things here, and if we could guess an analytic continuation, we could close our eyes and hope to be lucky and analytically continue the M theory terms to try to see what the behavior would be.
You'll be eventually see if there's M2 branes which also wrap internal directions that anchor around these 4 points that will contribute.
I see. Yeah.
Thank you.
Okay.
Any further questions? Well, let's thank Pedro once more.
Thank you.
And the next talk is at the top of the hour.